It's an odd thing to think about, isn't it? We spend so much time talking about stars, planets, and light. Yet, most of the Milky Way is made of the space between them, a sea of nearly nothing that somehow connects everything. When you look up at the night sky, you see islands of brightness separated by vast darkness. Your eyes and your mind tell you that the darkness is an absence, a pure and simple void. But what if your eyes are deceiving you? What if that emptiness is the most important part of the story? I wonder where you're listening from tonight. Maybe you're under the same stars we'll soon wander between. Maybe you're wrapped in a blanket, watching the slow dance of city lights through a window. Or maybe it's late, and you're somewhere quiet enough to imagine the sky stretching forever. Wherever you are, you're already part of this story. The atoms that make you were born in the very spaces we're about to drift through. If you find this calm, or curious, or just a gentle way to wind down, I'd be grateful if you'd give the video a like or maybe subscribe. It helps this little corner of calm reach others who might need a soft place to land too. Now, take a slow breath, settle your thoughts, and let's begin to question the very nature of the dark. Body. Between the stars lies a landscape that is neither empty nor still. It is the interstellar medium, the quiet ocean of gas and dust that fills the gaps between solar systems. Most people imagine outer space as a perfect void, a pure nothingness where not even dust dares to float. But that's only part of the story. The spaces between the stars are not empty. They're just incredibly thin. Imagine spreading a single grain of sand across a space the size of a football field. That's roughly how sparse the matter is out there. Yet, even that faint scattering of atoms and particles holds the history of the galaxy. When you look up at the night sky, what you see are islands of brightness, separated by vast darkness. But that darkness isn't an absence. It's a medium. Every photon that reaches your eyes has crossed those invisible seas. It's been bent, scattered, or softened by the faint gas and dust floating between solar systems. In some ways, the light we see from distant stars is a story about what lies between them. The interstellar medium, thin as it is, affects how light moves, how stars are born, and how galaxies evolve. Without it, there would be no stars at all. Let's imagine for a moment that you could drift freely beyond the edges of our solar system, past the outer planets, past the frozen Kuiper belt, past the Oort cloud, where comets sleep in their long, slow orbits. Eventually, you'd reach a boundary where the sun's influence fades, a bubble known as the heliosphere. Beyond that bubble lies true interstellar space, the domain of the galaxy itself. There, between one star and the next, you would find yourself surrounded by matter so thin you could travel billions of kilometers before colliding with a single atom. The density of hydrogen, the most common element in the universe, might be only 1 atom per cubic centimeter. In comparison, the air around you contains about 10 billion trillion molecules per cubic centimeter. The difference is almost impossible to grasp, yet even in this vast emptiness, something stirs. That something is not silence in the ordinary sense. It's not the stillness of a room after everyone has left. It's more like the silence of deep water, full of hidden motion, pressure, and faint currents. There are clouds of hydrogen gas drifting between stars, some cold and quiet, others warm and ionized by the light of nearby suns. There are filaments of dust winding through space, reflecting starlight in soft, ghostly hues. There are shock waves from ancient supernovae rippling outward, shaping the material that will one day become new solar systems. Every part of this interstellar ocean is slowly changing, slowly moving, though its pace makes glacial motion look hurried by comparison. If you could watch this space in fast motion, sped up 1 billion times, you'd see patterns emerge. Wisps of gas flowing toward regions of higher density. Shock fronts colliding. Giant clouds collapsing under their own gravity until they ignite, forming new stars. From afar, it would look like breathing. The galaxy inhaling and exhaling across millions of years. But to our human sense of time, these motions are imperceptible. We see the stars as fixed points, but they are drifting through the interstellar sea, each surrounded by its own invisible bubble of plasma and magnetic field. The sun moves too, carrying its planets with it, weaving through the galactic medium like a ship through calm, endless water. The idea that there is something out there, even between the stars, changes how we think about emptiness. The interstellar medium may seem thin, but it is full of meaning. The elements that make up planets, oceans, and living things, carbon, oxygen, nitrogen, iron, were all forged inside stars and released into space when those stars died. Over millions of years, those elements mixed with the interstellar gas, spread by winds, collisions, and supernova explosions. They drifted through space until gravity gathered them again into new systems. Every breath you take carries atoms that once floated in that ancient galactic night. If you could trace one of those atoms, say a carbon atom in your body, back through time, you might find it was formed in the heart of a massive star long before the sun existed. When that star reached the end of its life, it exploded, scattering its contents across the galaxy. That carbon atom may have wandered through interstellar space for hundreds of millions of years, joining clouds, escaping them carried by magnetic fields, before eventually settling into the gas cloud that gave birth to our solar system. Over billions of years, it found its way into Earth, into plants, into you. So even as you lie there now listening, your body carries the memory of what lies between solar systems. You are, in the most literal sense, made of the space between the stars. The distances between solar systems are enormous. Our nearest neighbor, the Alpha Centauri system, lies more than 4 light-years away. That's roughly 40 trillion kilometers. If the sun were the size of a coin, Alpha Centauri would be another coin several thousand kilometers away, with only a few wandering atoms between them. It's easy to feel small in that context, but also strangely connected, because despite the emptiness, those systems are linked by the same galactic environment. The dust that floats between them is shared material, shaped by the same forces, part of a single slow-moving ecosystem on a cosmic scale. The temperature out there depends on what kind of interstellar region you're in. Some areas near bright stars can reach thousands of degrees. Others in dark molecular clouds hover just a few degrees above absolute zero. Yet even at those frigid extremes, chemical reactions can occur, albeit very slowly. Molecules like carbon monoxide, ammonia, and water vapor can form on the surfaces of dust grains. In time, those grains clump together, gathering mass until they become the seeds of new stars and planets. So the emptiness between solar systems is not a void, but a nursery, a place where the next generation of worlds is quietly forming. Radiation moves through these spaces too, shaping them in subtle ways. Cosmic rays born from the violent end of massive stars stream through the galaxy at nearly the speed of light. They collide with atoms in the interstellar gas, ionizing them, altering chemistry, sometimes even triggering new waves of star formation. These particles are invisible to the eye, but they're one of the ways the galaxy keeps itself alive, recycling energy from death into new beginnings. The spaces between solar systems are not passive. They're dynamic, humming quietly with the echoes of creation and destruction. If you could somehow drift through interstellar space, shielded from the radiation and cold, you would see faint shifting colors in the distance, wisps of red and blue light from nebulae, the afterglow of ultraviolet radiation bouncing off dust. You might see dark patches, too, regions where dust clouds are so thick they block the starlight behind them. These are often the birthplaces of new stars. From the outside, they look like voids. But inside, gravity is pulling material inward, compressing it until nuclear fusion begins. The darkness between stars hides a quiet kind of activity that only becomes visible when new light is born. Our sun is not alone in drifting through this ocean. It's currently moving through a region known as the local interstellar cloud, a thin pocket of gas and dust roughly 30 light-years across. Before that, it may have passed through denser regions, and in the far future, it will move into others. These transitions can affect the outer boundary of the solar system, compressing or expanding the heliosphere. That means the conditions of interstellar space, its density, temperature, and magnetic fields, can subtly influence the environment here on Earth. Even across billions of kilometers, The edge of the galaxy is not some distant wall. It's all around us, gently brushing against the edges of our solar bubble. For all its thinness, interstellar space carries the fingerprints of countless events. Every supernova leaves behind shock waves that ripple through the surrounding medium. Every star emits stellar winds that push material outward. Over time, these forces carve bubbles, shells, and filaments in the galactic gas. The Milky Way, if you could see it without the glare of stars, would look like a complex web of glowing threads and empty pockets, a structure built by the combined breath of billions of suns. The space between solar systems is not random. It's sculpted, layered, full of quiet architecture. Astronomers study this invisible landscape using light in all its forms. Radio waves reveal cold hydrogen clouds. Infrared light shows where dust is warming near the young stars. X-rays trace the hot ionized gas left by ancient explosions. Together, these observations let us map the unseen terrain between systems, a kind of galactic weather report. The patterns we find tell us where new stars will form, where old ones have died, and how material moves through the Milky Way. It's humbling to realize that what looks like empty darkness to our eyes is, in reality, the connective tissue of an entire galaxy. And within that tissue, tiny motions accumulate. A molecule here, a dust grain there, moving slowly, colliding, joining, drifting apart again. Over time, these small actions shape the future. The interstellar medium is patient. It doesn't hurry. It doesn't rush toward creation. It waits quietly until the right conditions arise. A passing shock wave, a gravitational nudge, a subtle imbalance. And then, at last, a cloud begins to collapse, forming the bright point of a new star. From that star, a new solar system will form. And one day, perhaps another listener somewhere will look up and wonder what lies between. Out there, between the solar systems of our galaxy, the darkness isn't empty. It's a living canvas of atoms, radiation, and fields, all woven together in the slow dance of cosmic time. The journey between one star and the next may take tens of thousands of years, even at the speed of light. But in that distance lies the material that connects them. The dust, the gas, the magnetic threads, all part of a single continuous medium that makes the Milky Way more than a collection of stars. It makes it a whole. If you could drift endlessly away from the sun, further than the planets and comets, past the faint boundary of the heliosphere, you would find yourself surrounded by a darkness so deep that it seems to swallow thought itself. But this darkness isn't the kind that simply hides things. It's not an absence. It's a kind of quiet fullness, a place where light has traveled too far to remain bright, and where even the simplest forms of matter rest in slow motion. It is, in many ways, the ocean between stars, not made of water, but of time, distance, and the faint shimmer of scattered particles that never quite touch. People often imagine the space between solar systems as pure emptiness, a perfect vacuum where nothing at all exists. But emptiness is never truly empty. The darkness of interstellar space is more like a faint mist, stretched impossibly thin, a mixture of atoms, dust, radiation, and invisible magnetic lines that drift quietly through the galaxy. It's a kind of substance that's almost not there, but still enough to shape how the Milky Way lives and breathes. If the galaxy were a living organism, these dark stretches would be its bloodstream, carrying materials, energy, and quiet messages from one luminous organ to another. If you were somehow suspended in this vast darkness, you wouldn't see much with your eyes. The nearest star would appear as a sharp pin of light, its glow barely piercing the black. There would be no horizon, no up or down, just an endless depth of nothing that seems to go on forever. But if your vision could stretch across all wavelengths of light, radio, infrared, ultraviolet, X-ray, the emptiness would begin to reveal its texture. You'd see faint threads of gas glowing gently, delicate filaments shaped by distant forces. You'd see patches of thicker dust where starlight dims and reddens, the marks of future star nurseries. Even in darkness there is movement, and even in silence there is structure. The vast majority of our galaxy is made up of this quiet material, what astronomers call the interstellar medium. It's not a uniform fog, but a complex, uneven mixture of regions that vary wildly in density and temperature. Some areas are filled with hot ionized gas heated by nearby supernovae. Others are cold and dense, where molecules cluster together and begin the first stages of new star formation. Between them stretch long corridors of nearly perfect vacuum. The result is a patchwork of extremes, fiery and frozen, dense and diffuse, luminous and invisible, all coexisting in a slow, perpetual motion. To understand how delicate this medium is, imagine holding out your hand and trying to catch the air around you. In that space, there are roughly 10 billion trillion molecules per cubic centimeter. In interstellar space, there might be one atom in the same volume, maybe two if you're lucky. It's so empty that you could travel hundreds of kilometers before bumping into a single hydrogen atom. Yet, despite that sparseness, it's enough to scatter light, carry shock waves, and build the foundation of new worlds. On a cosmic scale, even the faintest traces of matter can add up to something enormous. Astronomers often describe interstellar space as being like an ocean because it behaves that way over vast distances. There are currents, not of water, but of charged particles and magnetic energy. There are waves, shock fronts, and tides formed by supernova explosions, stellar winds, and gravity. These forces slowly push, pull, and sculpt the gas between stars into immense shapes, giant clouds, filaments, and cavities that stretch for hundreds of light years. If you could see the Milky Way without its stars, you'd be left with something that looks like smoke frozen in time, a tangled web of dark and glowing threads suspended in a vast void. Light from distant stars travels through this medium, and along the way it changes. Some wavelengths are absorbed by gas atoms, leaving dark lines in the spectrum that astronomers can read like fingerprints. Other wavelengths are scattered by dust grains, giving distant starlight a faint reddish tint. This process, called interstellar reddening, is part of why some stars appear softer or dimmer than they truly are. It's the galaxy's way of reminding us that nothing travels untouched. Even the purest beam of light must pass through the quiet ocean and be shaped by it before it reaches another shore. If you could listen to this space, if somehow human hearing could translate electromagnetic whispers into sound, you'd hear a strange and constant hum. Not noise in the traditional sense, but a faint vibration. The combined murmur of particles colliding, fields shifting, and radiation moving through the dark. The Voyager spacecraft, now drifting beyond the edges of our solar system, have recorded faint plasma waves out there. These signals are evidence that space itself, even far from any star, is not dead. It resonates softly and continuously, like the low breath of the galaxy. There's something humbling about realizing that even this apparent emptiness holds its own kind of weather. There are winds in interstellar space, streams of charged particles flowing from hot stars or blown outward by supernova remnants. These winds travel for thousands of light years, shaping the clouds they encounter, compressing them, sometimes triggering the birth of new stars. It's an almost poetic symmetry, the death of one star sending the raw materials for the next into motion. The ocean between solar systems is both a graveyard and a cradle, filled with traces of what was and hints of what will be. Scientists studying this darkness use every tool available to decode it. Radio telescopes detect hydrogen's faint emission at a wavelength of 21 centipomaril, a soft glow that maps the invisible structure of the galaxy. Infrared observatories trace the warmth of dust clouds where new stars are quietly forming. X-ray satellites peer into the hot, ionized gas that fills the spaces between large clouds, remnants of long-dead stars. Piece by piece, they've built a map of a world we cannot see directly, a world that makes up most of our galaxy's mass and defines how it evolves. Inside this dark expanse, every particle matters. A lone hydrogen atom drifting through space may, in time, join others, forming a molecule of hydrogen gas. That gas might collect in a cloud, cooled by dust grains that radiate away heat. As the cloud thickens, gravity begins to tug on it more strongly, and the temperature at its core rises. After millions of years, the pressure becomes so intense that nuclear fusion ignites. A new star is born. The light that eventually shines from that star will travel across the same medium that once sheltered its beginnings. What seems like a quiet void is, in truth, the breathing space of creation. The darkness between solar systems is so vast that human minds struggle to grasp it. If our sun were reduced to the size of a marble, the nearest star, Proxima Centauri, would be another marble placed more than 700 kilometers away. Between them, nothing solid, just that faint ocean of gas and dust, almost imperceptible, yet everywhere. And scattered through that darkness are the memories of every star that has ever lived. Carbon, oxygen, silicon, iron. These elements drift together like ghostly plankton, waiting for the next tide of gravity to gather them into something new. The stillness of interstellar space is deceptive. It moves, but not in the way we do. It moves through pressure, temperature, radiation, and time. A shock wave from a distant explosion might take hundreds of thousands of years to cross a region. A molecule might spend 1,000,000 years slowly tumbling through cold space before colliding with another. Time flows differently there, not because of relativity, but because nothing hurries. It's a place where patience is the rule, and every motion is stretched thin across eternity. If you imagine the galaxy from afar, perhaps from some vantage point beyond its spiral arms, you'd see its light as a soft disk of faint shimmer. You might think that the darkness between the bright points is empty. But in truth, that's where most of the galaxy's story happens. It's where old stars give their matter back to space, and where new stars are gathering the pieces to form. It's where energy travels, dust circulates, and radiation finds its way. It's the connective tissue that keeps the galaxy alive. What makes this even more astonishing is how fragile it all is. The average density of the interstellar medium is so low that a small glass of air from Earth would contain more particles than a volume of interstellar space the size of a house. And yet without that faint mist, no star could exist. It's a reminder that the grandest processes often begin with the smallest ingredients. Atoms drifting in darkness, too subtle for us to see, yet capable of building everything. The darkness between solar systems also acts as a kind of memory field. Radiation from ancient supernovae still echoes faintly through it. Dust grains carry isotopes that tell stories about where they formed and what kind of stars gave birth to them. By studying these traces, scientists can reconstruct the history of our galaxy, when stars lived, when they died, and how their remains were mixed into the next generation. It's a kind of archaeology, but instead of shovels and brushes, astronomers use light itself to uncover what's buried in the dark. Even our own solar system moves through this environment like a ship through invisible water. The sun's magnetic field forms a protective bubble called the heliosphere, which shields us from much of the galactic radiation. Outside that bubble, interstellar particles drift freely. Occasionally, a few make their way inside, interacting with the solar wind and leaving faint traces that our spacecraft can detect. Through those traces, we learn that the dark ocean outside is not static. It changes as the sun moves through it, as the galaxy itself shifts and flows. If you were floating there in the darkness between solar systems, you might begin to lose your sense of scale. There are no landmarks, no boundaries, only the distant shimmer of stars. It would be easy to feel lost, but you'd also be surrounded by everything that connects those stars together, the dust that carries their remains, the gas that will feed their descendants, the faint magnetic threads that tie them into a single galactic web. You would be inside the structure that holds the Milky Way together. The darkness, instead of emptiness, would begin to feel like belonging. This space, this quiet ocean of darkness, is both the most desolate and the most fertile region of the cosmos. It's where nothing seems to happen, and where everything begins. Every planet, every moon, every living thing started here as part of this thin, drifting medium between stars. The silence of space isn't a void. It's a waiting room, a place where matter pauses between stories, where the next act of creation is gathering quietly out of sight. And so, when we look up at the night sky and see those points of light, it's worth remembering that most of what we're looking at isn't light at all. It's the dark in between, the vast, gentle ocean that fills almost everything. It's not empty. It's the space that holds the galaxy together, the space that gives birth to stars, the space that connects every atom we've ever known. The darkness between solar systems is not the absence of life or motion. It's the presence of possibility. If you could hold a piece of interstellar space in your hand, you wouldn't feel anything at all. No pressure, no texture, not even a hint of substance. You could reach out, close your fingers, and come away with nothing. That's because almost everything between solar systems is defined by absence. Not the absence of existence, but the absence of density. The thinness of everything out there is so profound that even words like vacuum fall short. We say space is empty, but the truth is far stranger. It's not empty in the way a room without furniture is empty. It's empty in the way a single breath of air spread across the distance between planets is empty. So empty that even the concept of emptiness starts to feel inadequate. The thinness of the interstellar medium is what makes it both invisible and essential. Most of the galaxy's volume is made up of this diffuse gas and dust. Yet its density is almost beyond imagination. Here on Earth, air is heavy. Every breath presses on your skin with the weight of the atmosphere above you, a sea of molecules packed together in endless motion. In space, that pressure vanishes. Between stars, a cubic meter of space may contain only a handful of atoms. In some regions, there might be just one. The average density of the interstellar medium is about 1 atom per cubic centimeter, an amount so small that if you gathered all the matter in a cubic kilometer, you'd have less than a grain of dust. And yet, that dust, that almost nothing, carries the ingredients of everything that will ever exist. If you could look closely enough at that 1 cubic centimeter, you'd find mostly hydrogen. It's the simplest, most abundant element in the universe, a proton with a single electron orbiting it. Mixed in here and there are helium atoms, remnants from the birth of the universe itself. And scattered among them are tiny traces of heavier elements: carbon, oxygen, nitrogen, silicon, iron, the ash of long-dead stars. Those atoms are few and far between, but they hold within them the entire story of cosmic evolution. They are the memory of what came before, and the seed of what will come next. The interstellar medium isn't the same everywhere. In some regions, the gas is cold, dense, and quiet, only a few dozen degrees above absolute zero. In others, it's hot and thin, energized by the blast waves of supernovae. This constant variation creates layers within the galaxy: the cold, neutral medium where new stars form, the warm, ionized medium, where ultraviolet light from massive stars strips electrons from atoms, and the hot intercloud gas, where supernovae stir the mix into chaos. Each of these layers has its own texture, temperature, and purpose, like currents in an unseen ocean. Together they shape how galaxies evolve and how stars are born, live, and die. But what does it mean for something to be this thin? It means that motion becomes slow. Collisions between atoms are rare events. A single hydrogen atom might travel for years, even centuries, before bumping into another. Heat, in the traditional sense, doesn't flow easily here. Instead, energy drifts across vast distances through radiation and magnetic fields. Pressure exists, but it's faint, like a whisper stretched across light years. To us, that seems like near nothingness. But to the galaxy, it's a delicate balance that keeps everything in motion. When astronomers measure this thinness, they don't just rely on counting atoms. They look at how light behaves as it moves through space. Certain wavelengths are absorbed by the gas, leaving dark lines in the spectrum of starlight. Those lines reveal what elements are present and how dense the space is between us and the star. By studying thousands of stars across the sky, scientists can map the invisible structure of the galaxy's interstellar gas, its filaments, bubbles, and voids. It's like tracing the veins of a leaf. by watching how sunlight filters through it. The dust between stars is even rarer than the gas, but it has an outsized effect. For every 100 atoms of hydrogen, there's roughly one tiny dust grain. These grains are made of silicates, carbon compounds, ice, and metals. Most are smaller than a single bacterium, yet they're crucial to the galaxy's chemistry. Dust grains act as tiny laboratories where molecules can form, where hydrogen atoms meet and combine into H2, or where carbon and oxygen come together to form complex organic molecules. In the thinness of interstellar space, solid surfaces are scarce, so dust becomes the meeting ground for chemistry to happen. When starlight passes through dust, it's scattered and absorbed. Shorter wavelengths, blue and violet light, are more easily blocked, which is why distant stars appear redder than they are. The same process makes nebulae glow with soft colors, turning ordinary light into something dreamlike. The thinness of space makes light behave differently, stretching, dimming, and shifting as it travels. Over distances of thousands of light years, these small interactions add up, painting the galaxy in subtle shades that tell us what lies in between. The thinness also has another, more practical consequence. It allows stars to move freely. Each solar system drifts through this sparse medium without much resistance. The Sun, for instance, travels at about 230 km/s around the center of the Milky Way. If the galaxy were filled with dense gas, that motion would slow down, drag would accumulate, and the stars would spiral inward. But because space is so incredibly thin, a star can glide through it for billions of years without losing momentum. The emptiness preserves motion, allowing galaxies to maintain their graceful rotation. Even so, the interstellar medium isn't entirely passive. When a supernova explodes, the blast wave sweeps up the surrounding gas, compressing it into dense shells. These expanding bubbles of energy carve out enormous cavities in the thin material, leaving behind what astronomers call superbubbles, regions tens or hundreds of light years wide, filled with hot, ionized gas. Over time, these structures merge, forming a kind of frothy texture across the galaxy. The Sun itself currently drifts through one such region, a local bubble created by ancient supernovae long before our solar system formed. It's an invisible legacy of explosions that happened before Earth even existed. Inside that bubble, the thinness is extreme. The density of matter is lower than the already faint average of the galaxy. Yet even here there are traces, a few atoms per cubic centimeter, a dust grain every few meters. It's easy to overlook how extraordinary that is. Those scattered particles have been traveling for millions of years, shaped by radiation, twisted by magnetic fields, occasionally colliding, joining, or splitting apart. They've been everywhere, from the cores of dying stars to the outskirts of galactic arms. The thinness of everything means that motion never truly stops. It just slows until it becomes invisible to us. Temperature, too, takes on strange meaning in such a place. In everyday life, temperature is a measure of how fast atoms move and collide. But when collisions are rare, that definition begins to blur. The gas between stars can have temperatures of thousands or even millions of degrees, but because the density is so low, it wouldn't feel hot. There aren't enough particles to transfer heat to your skin. It's like being surrounded by a warm wind that never actually touches you. Temperature, in the thinness of interstellar space, becomes more of a description of energy than of sensation. The thinness also affects time in subtle ways, not in the relativistic sense of Einstein's equations, but in how change unfolds. Processes that happen in seconds on Earth can take centuries in interstellar space. Chemical reactions proceed slowly because the participants almost never meet. Clouds of gas take millions of years to collapse into stars. Even light, the fastest thing there is, needs thousands of years to cross the vast distances between systems. The thinness stretches time until everything seems to move in slow motion. It's a place where patience is the only constant. Still, despite that patience, the interstellar medium is not static. It breathes. As stars form and die, They push material outward, which later cools and falls back in elsewhere. It's a galactic recycling system, slow but steady. Each generation of stars enriches the medium with heavier elements, and those elements, in turn, form planets, moons, and perhaps life. The thinness of everything makes that cycle possible. It allows material to travel freely, to spread and mix without clumping too quickly. It ensures that the galaxy remains dynamic and creative instead of collapsing into stillness. If you could watch the Milky Way over billions of years, you'd see the thin interstellar gas flowing like a tide between its spiral arms. You'd see supernovae flare, their shock waves spreading out like ripples on a pond. You would see clouds forming, stars igniting, and then eventually those stars returning their material to the void. The galaxy would look like a single slow organism, breathing in and out, sustained by the thinness of its own substance. The space between solar systems, far from being dead, is the bloodstream that carries this slow rhythm forward. Our own solar system interacts with that thinness constantly. The solar wind, a stream of charged particles from the sun, pushes outward, carving a bubble in the interstellar gas. Where the solar wind meets the galactic medium, it forms a boundary called the heliopause. Beyond that, the sun's influence fades, and the true thinness of interstellar space begins. The Voyager probes crossed this boundary years ago, and their instruments confirmed what scientists had long suspected. Even out there, far from any star, there is still something. A whisper of particles, a trace of magnetism, the faint hum of the galaxy's plasma. When you think about the scale of it all, it's astonishing that such an environment could hold meaning for us. But it does, because everything we are began in that thinness. Every carbon atom in your body once drifted freely between stars. Every oxygen atom you breathe once existed in that invisible medium before it became part of a cloud, a star, a planet, a cell. The thinness of everything is not a void to be feared. It's the foundation from which all substance emerges. Without it, the universe would have no room to grow. So, the next time you look at the night sky and see the stars hanging in darkness, remember that the darkness is not an absence. It's a structure so delicate that it defies imagination. A single hydrogen atom adrift in space may seem insignificant, but multiply it by the vastness of the galaxy, and it becomes a network connecting every star to every other. The thinness of everything is what holds the cosmos together. It allows light to travel, matter to move, and time to unfold. It's the invisible stage upon which every act of creation quietly takes place. The galaxy's beauty depends on its thinness. Too dense and it would collapse into chaos. Too empty and nothing could form. It's the balance between nothing and something that makes everything possible. Out there, between solar systems, that balance stretches endlessly, shaping the Milky Way's slow pulse, holding the stars apart just enough for life to happen, just enough for wonder to exist. And in that thought, the silence between worlds begins to feel not lonely, but necessary, the thin breath of the universe, steady and eternal, waiting patiently between the stars. I asked you to consider what might be floating in this vast, dark sea. The answer is both simpler and more complex than you might imagine. It is an ocean made of almost nothing, a breath so thin it defies the very concept of substance. Yet, within this near-nothingness, the entire story of our galaxy is written. It is the raw material of existence patiently waiting. But how can something so diffuse, so barely there, hold such power? How can a whisper build a world? If the darkness between stars is an ocean, then the interstellar medium is its water. It is the fundamental substance, the fluid of the galaxy. And like any ocean, it is not uniform. It has currents and depths, warm shallows and freezing abyssal plains. It has a composition, a texture, a behavior all its own. Let's begin with its primary element, the hydrogen that makes up the overwhelming majority of this cosmic sea. Imagine the simplest thing you can. A single proton, a single electron dancing around it. This is a hydrogen atom. Out in the deep space between solar systems, these atoms are the solitary swimmers. They are so far apart that each one is, for all intents and purposes, alone in its own immense universe. A single atom might travel for years, decades, even centuries in a perfectly straight line before it comes close enough to another to interact. This isolation defines the nature of the medium. It is a realm of solitude and slow, patient motion. But this hydrogen is not all the same. It exists in different states, different phases, depending on the local environment, the temperature, the pressure, the proximity to stellar energy. Astronomers, in their need to categorize the cosmos, have given these phases names that sound like the movements of a silent symphony: the cold neutral medium, the warm neutral medium, the warm ionized medium, and the hot ionized medium. First, the cold neutral medium. Picture the deepest, darkest parts of the ocean, where sunlight never penetrates. Here, in the dense cores of molecular clouds, the hydrogen gas is cold, only a few tens of degrees above absolute zero. It is so cold and still that the atoms, in their slow dance, can pair up. They form molecules H2, molecular hydrogen. This is the quietest, most reserved state of the interstellar sea. It is the state of rest, of gathering, of potential. In these cold, dark regions, the dust also gathers, and together this cold gas and dust form the maternity wards of the galaxy. They are the nurseries where the next generation of stars is quietly, secretly beginning to form. The silence here is not empty, it is pregnant. Then there is the warm neutral medium. This is the bulk of the interstellar ocean, the great sprawling plains between the dense clouds. Here the hydrogen is still neutral. Its protons and electrons remain paired, but it is warmer, stirred by the faint energy of distant starlight or the passing shock waves of ancient explosions. The atoms move a little faster. They are a little more spread out. If you were drifting through this region, it would feel like the open sea on a calm, overcast day. There is a pervasive grayness, a sense of being in the middle of something vast and featureless. This is the background state of the galaxy, the default setting of the space between the bright islands of stars. But starlight, especially the fierce ultraviolet light from massive young stars, does more than just warm the gas. It can be violent. It can strip the electrons right off the hydrogen atoms. This process creates the warm ionized medium. Here, the hydrogen is no longer neutral. It is a plasma, a soup of free-floating protons and electrons. This ionized gas glows faintly, emitting a specific red light that astronomers can detect. These are the HII regions, the great glowing nebulae like Orion that we see in telescopes. They are the parts of the ocean that have been energized, set ablaze by the intense radiation of newborn suns. They are hotspots of activity where the galaxy's creative forces are on full display. And finally, there is the most energetic phase, the hot ionized medium. This is the gas that has been heated to millions of degrees by the violence of supernova explosions. It is incredibly thin, even by the standards of the interstellar medium, but it is seething with energy. This gas doesn't pool in clouds. It fills the vast cavities and bubbles blown by dying stars. It is the steam rising from the galactic forge. The sun, as it travels, is currently moving through a region of this hot, thin gas, the local bubble. We are, right now, inside a supernova remnant, a ghost of a stellar catastrophe that occurred millions of years ago. We are sailing through the lingering breath of a long-dead star. This patchwork of phases, cold, warm, ionized, hot, is not static. It is a dynamic, ever-changing system. A shock wave from a supernova can compress a cloud of warm, neutral gas, triggering its collapse into a cold, dense molecular cloud. The birth of massive stars within that cloud can then ionize the surrounding area, creating a bright HII region whose radiation and winds will eventually blow the cloud apart, returning the material to the warmer, more diffuse medium. It is a cycle, a continuous, slow-motion churning of the galactic waters. The sheer scale of this ocean is, once again, almost incomprehensible. A single one of these molecular clouds, these stellar nurseries, can be hundreds of light years across and contain enough material to form 10,000 suns like our own. The pillars of creation immortalized by the Hubble telescope are but a tiny picturesque corner of a much vaster structure. We are talking about continents of gas and dust adrift in the galactic sea, and within this sea, the dust is the silt, the fine powder suspended in the water. For every 100 or 1,000 atoms of hydrogen, there is one microscopic dust grain. These grains are tiny, most smaller than a wavelength of light, but they are crucial. They are not simple dirt. They are complex particles, often with a silicate. Rock core and a mantle of ices, water ice, carbon dioxide ice, ammonia ice. They are the only solid surfaces for light years around. It is on the surfaces of these dust grains that the magic of chemistry begins. In the near-perfect vacuum of space, two hydrogen atoms floating freely will almost never form a molecule. They need a third body to absorb the excess energy of their bonding, a dance floor, as it were. A dust grain provides that dance floor. The atoms stick to its cold surface, they shuffle around, and when they find each other, they can link up to form molecular hydrogen, H2. This is the first, most fundamental step in building complexity from simplicity. Without dust, the cold clouds could not cool efficiently, and the formation of stars would be much more difficult. Dust is the catalyst, the facilitator of creation. This dust also shapes the light that travels through the ocean. As starlight passes through a cloud of dust, the tiny grains scatter the shorter, bluer wavelengths of light more effectively than the longer, redder ones. This is why the sun appears red at sunset, the same process on a vaster scale. A star seen through a long stretch of dusty space will appear redder and dimmer than it truly is. This interstellar reddening is a veil that the galaxy places between us and its most distant lights. It is the ocean's tint, a filter of fine cosmic sediment. But the dust does more than just block and redden. It also glows. The same grains that absorb the energetic light from stars warm up by a few tens of degrees above absolute zero. And like any warm object, they re-emit that energy, but as infrared light. If our eyes were sensitive to infrared, the Milky Way would not appear as a band of stars, but as a band of glowing dust clouds, a river of soft, warm light winding through the sky. The darkness is, in truth, a glow with a heat we cannot feel and a light we cannot see. All of this, the hydrogen in its various forms, the dust grains, the magnetic fields that thread through it all, creates a system of incredible complexity. It is a fluid, but a fluid unlike any on Earth. Its dynamics are governed not just by pressure and gravity, but by magnetism and radiation. There are currents in this ocean. Vast streams of gas flow along the spiral arms of the galaxy, guided by the gravitational tides of the galaxy itself. There are waves, sound waves, shock waves, magnetic waves that ripple through the medium, transferring energy from one place to another over millions of years. This ocean has weather. There are calm doldrums in the cold, dark clouds. There are high-pressure systems in the hot, ionized bubbles. There are storms, not of wind and rain, but of particles and radiation, unleashed by supernovae. The Voyager probes, now in interstellar space, are our first buoys, our first weather stations, sending back data on the conditions in this uncharted sea. They have detected the faint hum of plasma waves, the gentle lapping of the galactic tide against the hull of humanity, and we, like all solar systems, are sailing ships on this ocean. The sun moves through the local interstellar cloud, its heliosphere, acting as a kind of prow, pushing the interstellar gas aside as we travel at 230 kilometers per second around the galactic center. The conditions outside our bubble change, and so the size and shape of our protective shield change with it. We are not separate from this environment. We are immersed in it, moving with its currents, feeling its subtle pressures. The interstellar medium, this ocean between the stars, is the galaxy's circulatory system. It carries the elements forged in stellar cores and scattered by supernovae. It transports energy from places of violent death to places of quiet birth. It is the medium through which the galaxy breathes, inhaling diffuse gas and exhaling new stars. It is the reservoir from which everything is drawn, and to which everything, one day, will return. The atoms in your body, the iron in your blood, the calcium in your bones, the oxygen in your lungs, they have all been part of this ocean. They have drifted in the cold darkness. They have been warmed by starlight. They have been swept up in shock waves. And they have clung to the surface of a dust grain, waiting for their moment to become part of a new story. You are not just a visitor to this cosmos, looking out at a distant sea. You are a part of the sea itself, temporarily gathered into a form that can wonder about its own origins. So, when you look up at the night sky, try to see beyond the points of light. Try to feel the presence of the ocean that surrounds them. It is an ocean of whispers, of faint glows, of patient potential. It is the great connector, the substance that makes the Milky Way a single, coherent entity, rather than just a collection of isolated fires. It is the quiet, dark water from which all light is born. To understand cosmic dust is to become a cosmic historian. It is to learn to read the universe in grains of sand smaller than a wavelength of light. Each one is an archive, a tiny, rugged vessel sailing the interstellar ocean, carrying a story billions of years old. Let's begin at the end of a star's life. This is where the dust is forged. Picture a star, not like our sun, but a massive giant, many times more massive. For millions of years it has burned brightly, fusing hydrogen into helium in its core, then helium into carbon and oxygen, in a layered, desperate struggle against the crush of its own gravity. It becomes a cosmic onion with iron, the ash of nuclear fusion, piling up at its heart. Iron is a dead end. It cannot be fused to release more energy, and so the star's internal support system fails. In a fraction of a second, the core collapses. The outer layers, with nothing to support them, come crashing down at a quarter the speed of light, only to rebound off the newly formed, impossibly dense neutron star at the center. A shock wave of unimaginable power ripples outward. The star explodes. This is a supernova. For a few weeks, it can outshine an entire galaxy. In this cosmic inferno, in this maelstrom of energy and newly forged elements, the raw atoms are seared together. In the expanding, cooling fireball, in the chaotic wind streaming from the dying star, atoms of silicon, carbon, iron, and oxygen collide and stick together. They form tiny solid clusters. They are the first seeds of dust, born from the very heart of the explosion. But supernovae are not the only forges. There's a slower, more gentle kind of dust production. Consider an aging star, a red giant in the final stages of its life. It has exhausted the hydrogen in its core and now burns helium in a shell around a core of carbon and oxygen. It becomes unstable, pulsating, its outer layers swelling to encompass the orbits of the inner planets. In these cool, extended outer layers, far from the fusion fires of the core, conditions are just right. Atoms of carbon, silicon, and other elements, freshly cooked in the star's interior and dredged up to the surface, can condense. Like soot forming in a candle flame, they coalesce into solid particles. The star's own gentle stellar wind, flowing outward for thousands of years, carries these newly formed dust grains away, scattering them into the interstellar medium like a gardener sowing seeds. This is a quieter, more prolonged farewell, a slow exhalation of a star's substance back into the galaxy. So dust is born from both violent death and serene old age. But its journey is only beginning. Once freed from its parent star, a dust grain embarks on an epic voyage. It is pushed by the gentle pressure of starlight, a force so faint we never feel it on Earth, but over the vast emptiness of space, it is enough to propel these tiny sails. It is swept up in the currents of the interstellar medium, the flows and tides we discussed before. It will wander for millions, sometimes billions of years. Its life is one of constant peril and transformation. It might drift into a cold, dark molecular cloud, finding temporary shelter. There, in the deep freeze just a few degrees above absolute zero, it will act as a meeting ground. Icy mantles of water, carbon monoxide, and ammonia freeze onto its surface. It becomes a tiny frozen laboratory. Hydrogen atoms, skittering across its surface, find each other and link up to form molecular hydrogen, the fuel for future stars. More complex molecules, prebiotic organic compounds, can form in these icy layers. The dust grain is no longer just a mineral, it is a chemical factory, a crucible for the building blocks of life. But this sanctuary is temporary. A nearby star may ignite, its fierce ultraviolet radiation blowing the cloud apart, vaporizing the icy mantles and blasting the bare grain with energetic photons. This is sputtering, a slow, relentless sandblasting that can erode the grain over eons. Or the grain might be caught in a shockwave from a distant supernova, accelerated to tremendous speeds, and shattered in a collision with another grain. Its components are returned to the gas phase, only to perhaps condense again somewhere else in some other form. The life of dust is a cycle of destruction and rebirth. It is constantly being made in the death throes of stars and constantly being destroyed by the very energy of those who live. It is the galaxy's way of recycling itself, of stirring the pot. This cycle enriches the interstellar medium. The first stars in the universe, population 3 stars, were made of pure hydrogen and helium. They lived fast, died young, and in their explosions, they forged the first heavy elements, the first carbon, the first oxygen, the first silicon. They polluted the pristine cosmic gas with the ashes of their death. The next generation of stars formed from this enriched material, and they in turn forged even heavier elements. With each stellar generation, the galaxy became dustier, more complex, more capable of forming rocky planets and, ultimately, life. We are the beneficiaries of this long chain of cosmic inheritance. Our solar system formed from a cloud of gas and dust that had been enriched by countless generations of stars that lived and died before the sun was born. The evidence for this is literally written in the rocks. Inside certain primitive meteorites, the ones that have remained relatively unchanged since the dawn of the solar system, scientists have found pre-solar grains. These are microscopic diamonds, silicon carbide, graphite, and corundum grains that are older than the sun itself. They are unaltered stardust, time capsules from other stars. How do we know? Every element comes in different varieties, called isotopes, which have different numbers of neutrons in their atomic nuclei. The precise ratios of these isotopes are like a fingerprint. The fusion processes inside a star and the violent conditions of a supernova create very specific and unusual isotopic signatures. When we analyze these presolar grains, we find isotopic ratios that are completely alien to our solar system. They could only have been formed in the heart of a specific type of dying star. We are, quite literally, holding pieces of other suns in our hands. We are sifting through the galactic archaeological record grain by tiny grain. This dust is not just a relic. It is an active and essential player in the galaxy's evolution. Its most crucial role is in the birth of stars. A cloud of pure hydrogen gas, if compressed, will heat up. The increased pressure from this heat can resist further collapse, preventing the cloud from forming a star. But dust changes everything. Dust grains are incredibly efficient at radiating away heat. As a cloud collapses, the dust inside it absorbs the gravitational energy and re-emits it as infrared radiation, which escapes easily into space. The cloud can cool. With the thermal pressure reduced, gravity wins. The cloud can fragment and collapse further, eventually forming the dense cores that ignite into stars. Without dust to cool the gas, star formation would be a much slower, more inefficient process. The galaxy would be a darker, simpler place. Dust also shapes the light we see. It is the reason we cannot see the center of our own Milky Way in visible light. Great lanes of dust, thousands of light years across, block our view. They are the dark rifts in the summer Milky Way, not voids, but towering opaque clouds. Yet, when we switch to infrared telescopes like Spitzer or James Webb, the picture changes dramatically. Infrared light passes through dust almost unhindered. The dark lanes burst into light, revealing a hidden universe of stellar nurseries, clusters, and structure. Dust, which hides the universe in one light, reveals it in another, and it is within these dusty cocoons that the final act of the dust's story unfolds, the formation of planets. Around a young star, the leftover gas and dust form a spinning disk, a protoplanetary disk. Within this disk, the dust grains are the seeds of everything to come. They collide, they stick, they form fluffy aggregates. These aggregates grow into pebbles, then rocks, then planetesimals, the building blocks of planets. Through a process of accretion and collision, these planetesimals coalesce into terrestrial planets like Earth, Mars, and Venus. Every mountain, every riverbed, every grain of sand on a beach was once part of this interstellar dust. The iron in the Earth's core, the silicon in the rocks, the carbon in our bodies, it was all part of that great cycle of death and rebirth. The dust that once drifted between the stars, that witnessed the death of its parent star, that traveled for eons through the galactic dark, finally found a home. It gathered together, warmed by a new sun, and became part of a world where it could eventually look up and wonder about its own origins. This is the profound connection. You are not just living in the universe. You are literally made of it. The calcium in your bones was forged in the heart of a massive star that exploded billions of years ago. The oxygen you breathe was released by a dying red giant. The carbon that forms the backbone of your DNA was created in the triple alpha process in a stellar core. You are a collection of ancient stardust, temporarily assembled into a form that can contemplate the stars from which it came. The dust that dreams are made of is not a metaphor. It is a fact. It is the deepest truth of our cosmic identity. We are the universe become aware of itself. The ghosts of long-dead stars live on in us, in our thoughts, in our curiosity, in our drive to understand the dark from which we emerged. So, the next time you see a shaft of sunlight illuminating dust motes dancing in the air, pause for a moment. See them not as nuisance, but as symbolism. They are a tiny local echo of the great cosmic process. They are a reminder that the same principle of matter gathering, of small things coming together, operates from your living room to the spiral arms of the galaxy. We are surrounded by dust, we are made of dust, and to dust we shall return, not as an end, but as a promise of reformation, of another journey through the silent, creative dark. For any single atom, this event is incredibly rare, happening only once every several million years. But space is vast, and hydrogen atoms are numberless. Across the immense distances of the galaxy, these infinitesimally rare events add up into a constant, detectable signal. It is a whisper that builds into a chorus. By tuning our radio telescopes to this 21 kilometer line, we can literally listen to the structure of the galaxy. We can map the vast, swirling arms of neutral hydrogen that define the Milky Way's spiral architecture, tracing currents and flows that are completely invisible to optical telescopes. This whisper is the primary way we hear the galaxy's skeleton. But hydrogen is a versatile element. Its whisper changes depending on its environment. In the cold, dense embrace of molecular clouds, where atoms are close enough to meet and bind, hydrogen pairs up. It forms H2, molecular hydrogen. This is a different kind of silence. Molecular hydrogen is very poor at emitting radiation. It is a quiet, secretive state, huddling in the dark. To find these hidden reserves, the true raw material for star birth, we must listen for other tracers, like carbon monoxide, that mingle with it and sing more readily, revealing the locations of these stellar nurseries. In other regions, the whisper becomes a shriek of light. Near hot, massive stars, The intense flood of ultraviolet radiation is violent. It slams into the neutral hydrogen gas, stripping electrons from their protons in a process called ionization. What was once a quiet neutral atom becomes a seething energetic plasma, a soup of free protons and electrons. This is the birth of an HII region, and this region is not silent. The chaotic energized electrons and protons inevitably recombine. When an electron is captured by a proton, it doesn't just settle down quietly, it cascades down through energy levels, emitting photons of specific colors as it goes. One of the most prominent is a characteristic red glow, the magnificent Orion. Nebula, that glowing sword in the winter sky, is fundamentally a vast cloud of ionized hydrogen screaming in the visual light we can see. It is the whisper of the gas, amplified by stellar fury into a brilliant shout. Yet even this shout is temporary. The very stars that create these glowing nebulae will, in a few million years, explode as supernovae. Their final acts blast away the surrounding gas, dispersing it back into the general medium, where it will cool, quiet down, and eventually return to the neutral, whispering state, ready to begin the cycle again. This is the true nature of the galactic raw material. It is a continuous, cyclical conversation. The gentle whisper of the widespread neutral hydrogen is the default state, the reservoir of potential. It gathers into dense, silent molecular clouds. The ignition of new stars within them turns their silence into a brilliant but short-lived shout of light, and the death of those stars returns the material to the whisper, now enriched with heavier elements, ready to form the next generation. This gas is the breath of the galaxy. It is the substance from which stars inhale their mass. It is the medium through which they exhale their energy and their newly forged elements. We are not separate from this flow. The hydrogen in the water molecules of your body has passed through this cycle. It has whispered between stars. It has been part of a glowing nebula, and it has been gathered by gravity to become part of our world and part of you. You are not just living in the galaxy. You are breathing its fundamental substance. The whisper of the interstellar gas is not just a sound from far away. It is the echo of your own origin. End with question. We have now heard the voice of the galaxy's primary substance, the whisper of hydrogen that maps the darkness, the brilliant shout of its ionized regions, and the deep silence of its molecular cradles. This gas is the fluid of the interstellar ocean. But a fluid does not move without guidance. Its currents are shaped by invisible banks and channels. So, what are the unseen forces that sculpt this flowing, whispering sea? What invisible rivers guide the very breath of the galaxy?